So first of all, is everyone comfortable with Bengali or with English? Bengali. Is there anyone in the audience who doesn't understand Bengali? Okay. So then what I will try to do, I will talk in English, but you can ask question in Bengali, and this topic is actually a little bit advanced, so I'll try to go as slow as possible, and you can interrupt me at any point of time. I planned something, but it's not necessary I have to cover entire thing that I planned. So first of all, it's my great privilege and honor to give this talk in this platform, and Ramakrishna Mission has, and the Gold Park has a special place in my mind, so that's why I'm indeed honored and privileged. So the topic of today's talk is quantum materials. What I mean by quantum materials will be clear in few slides, because many people may not know this name called quantum materials. And I come from this institute, which has been already announced, is S.N. Bose National Center for Basic Sciences, which was established in the year 1986 by the funding agency Department of Science and Technology, which is under the Ministry of Science and Technology, to honor the life and work of Professor Satyendranath Bose. So how many people in this audience have heard the name of Professor Satyendranath Bose? I think many. So that's actually already a very good starting point. So I just took it from Wikipedia. If you go and type Professor Satyendranath Bose, you will get it. It's the father of God particle. So how many of you have heard the name God particle in recent time? Many of you. So what is that? Any idea? Higgs boson. Higgs boson was actually said as God particle. But the word boson is actually due to Bose, and it was due to the statistics which is known as Bose-Einstein statistics. Einstein is a very famous physicist. I am sure everyone in this hall has heard his name. So these two scientists, one from India and another from Germany, they got connected through this Bose-Einstein statistics. And actually I will tell you a little bit genesis of their interaction. And the name boson was actually given by Paul Dirac, because in his name there are some other kind of particles which are known as fermions, and there is a Dirac fermion theory. So this name was given by him that these particles should be called as bosons. I will tell you a little bit what are these bosons. For some reason it's not working this way. So I have already told you about this Bose-Einstein statistics, because S.N. Bose is world famous because of this Bose-Einstein statistics. You know, we live in this world which is a classical world. Everything we see here actually has a classical description, because we are all at some room temperature. So there is always some thermal fluctuation. Is it okay? Everyone is with me? Okay. So we have some thermal fluctuation. But suppose I have a means to cool down everything and stop this thermal fluctuation. Then the world will be governed by the laws of quantum mechanics, which is very different from this classical world. And a lot of new things started happening. For example, as a classical particle, if you put a barrier in front of me, having the probability of me in the other side of the barrier is actually 0, because there is a barrier in front of me which I should not be able to cross. And if you measure really the probability, what is the probability of finding me at the other side, is actually 0. But if I were a quantum particle, there would have been always a finite probability. It might sound mysterious, but quantum mechanics actually is mysterious. It allows a finite probability to be at the other side. Similarly, I am here. Since I have a finite probability to be here, I am like a particle. On the other hand, depending on this situation, if quantum mechanics takes over, then same me can also be seen as a wave. So these all might seem, I don't know, maybe some of you are Bengali here. So in Sukumar Rai there was a concept called Hasjadu, which is neither this nor that. And quantum mechanics is really like that. A same object can behave as a particle, also can behave as a wave, depending on the situation. And in fact, in 1924, and next year is going to be the centenary of this very famous paper. And our institute, S.N. Bose Center, is going to celebrate it in a big way, and we will organize public lecture. So please, there will be advertisement in the newspaper so that you can come and join such public lecture. So Bose actually was not very happy with this black body radiation of Planck, which actually was based on some kind of this classical concept. And he actually gave a new interpretation to it, which required the concept of quantum mechanics, and sent to this journal called Philosophical Magazine. The paper got rejected. So in this audience, irrespective of whether you are scientist or not, many things you want to do in life, you may be rejected. But there is nothing to be disheartened. Rejection is just not the end of life. And it has happened to many great people. It has happened also to S.N. Bose. So the paper got rejected. He then sent it to Einstein with a covering letter, because although he knew German, he was not very confident, because he wanted to actually send this paper to this German research journal, Zeitschrift für Physik, but which actually publishes paper in German. And he, although he knew German, he was not very confident to translate it to German and then send it to the journal. So instead of that, he sent it to Einstein. And you can see those days how the communication took place. No writing in email, fax, nothing. It was a handwritten thing. And in a couple of weeks, Einstein's reply came, because he actually understood the prospect of it. He translated and got it published in the journal which Bose dreamed of publishing. And this was Einstein's covering thing to the journal. It says, in my opinion, Bose's derivation signifies an important advance. He could actually see it there. The great people, they resonate, they appreciate each other. The method used here gives quantum theory of an ideal gas, as I will work out elsewhere. And that's what made it a Bose-Einstein statistics, which is a kind of a general thing, not only about this black body radiation. And this is what is shown here, something what is called distribution. If you have number of particles, then depending on their energy, you can distribute them. And I just mentioned the classical world. If you are a classical particle, then you will actually follow what is shown here as a black line. But on the other hand, if you are a quantum particle, as I said, that if you get rid of all this thermal fluctuation, okay, then I am in this quantum world, and then depending on, so each of these particles can have a spin, okay? They can spin either this direction or that direction. At that spin, I am using a little bit technical term, can be integer or half integer. Depending on that, you also have a distinction between quantum particles. So some of the particles follow the famous Bose-Einstein statistics, and they are called bosons, while the others, the Fermi-Dirac statistics. For example, if I was an electron, you have heard the name electron, I think all of you, that will follow the Fermi-Dirac statistics. But on the other hand, if I take light, for example, and really look at its quantum nature, I will have some particles which are known as photons. And those photons will actually have a different distribution, which is shown with this blue line. So it's all about how exactly this particle distribute as a function of energy. So is there any question so far? At any point of time, you can stop me and ask question. And within Bose Center, we have a really nice archive and museum on Bose. I showed you some of these postcards, handwritten. The originals, if you visit our center, you will be able to see. And in fact, it was featured in Telegraph. And right now, even if you go to the website of our center, there is a virtual tour of this museum. So you can just click there, you can see the museum, and if you are interested, you can visit us. The day to visit our institute is the open day. The birthday of Bose, Professor Bose, is 1st January. So therefore, in the first week of January, an advertisement is given in newspaper, we actually celebrate an open day. Anyone interested in science, you don't need to be scientist, you just need to be interested about science. You can come and visit our center. There is a registration because no fee, just to register your interest, because we can't accommodate everyone, so we have some cutoff. And what is organized, it's a whole day program. We normally have a popular science talk, very often given in Bengali, and visit to all the science lab we have, visit to this Bose archive that I just mentioned, and we also have a sky watching in the evening. So it's a whole day program, and so January 2024 is not very far, so in advance I'm giving you some notice. So is there any question so far? Because now I will get into somewhat technical stuff. So the gravity normally is a classical concept, but there is also something called a quantum gravity, but the Earth's gravity that you are thinking of is actually a classical concept. Maybe we can discuss little later because I don't get your question quite. Reference frame. So the reference here is actually, so every particle has a quantum nature, but the thermal fluctuation, the temperature at which you are working, that decides whether this object will behave really like a classical or quantum. So temperature scale, you can think it as an energy scale. So that is the scale if you are talking about. Similarly, there is what is known as the size. If you go down and down in size, actually you are reducing many of this thermal fluctuation, and you will be able to see that effect. So to scale, if you are talking about the scales, then one is of course the energy scale, other is also the time scale. the size, the length scale. So with that, I will try to come to the main topic, and this being technical, I will try to describe as simple manner as possible, but I can't simplify things too much because then the rigor will also go. So you must have heard the thing quantum technology. Have you heard? Yes, it's very much in news in recent time. And it is a worldwide thing. It's not only in India, it's worldwide. How could quantum technologies transform our society? And what I have shown is basically some example of this worldwide activity, and this is just few representative. There are actually many more than it. So CIFAR, which is actually the prime funding agency in Canada, they have put forward scientists from different parts of the world to address such kind of question. There is a center which is actually the Max Planck, which is in Germany, University of British Columbia in Canada, University of Tokyo. So you can see people from different parts of the world, the scientists from different parts of the world, they are working together to answer some of this, the question that I have shown here. And this is another which is in US, which is funded by NSF. And India is not lagging behind. This is a news a couple of years back, but that time already our finance minister announced that there will be a big investment in what they called as a national quantum mission. And this year, the minister has made it more official with a more concrete plan and with a press release, and India will work hand in hand also with US on such a kind of quantum mission. So how many of you have heard the word quantum computing? You know the computer. Every one of us know the computer. So that's a classical computer. You use some bit which can be either 1 or 0, right? So that's, I just said, like a classical thing. Everything is definitive, 1 or 0. But if it was quantum, you could have actually created infinity of states between 1 and 0, because you can take a part of 1, take a part of 0 and mix them. So quantum computing is a completely new concept which will harness the properties of quantum state, that there are infinity of states between 1 and 0. It's not definitive. And can use what is known as superposition. I can superpose a fraction of 1 and a fraction of 0 and create a new state. So the idea currently is, if you can have such quantum computer, and already some small scale quantum computers have been already made, so that will revolutionize the way you think of. For example, if you think of the COVID time, all this, there was a lot of drug designing. Drug designing requires a lot of computation. If instead of a classical computer, if you can take the help of quantum computer, maybe the way of drug designing will be revolutionized. So that is the kind of idea or the motivation with which such quantum computing concept started. It is still not very clear. For example, you know, for your classical computer, behind it you have a semiconductor industry, right? There should be a hardware. All you see, all your laptop, everything has a hardware in it. So what will be the right platform for quantum computer? What will be the hardware? So still people are debating on it. Some of the ideas are like supercomputing, a superconducting loop. I will come what is a superconductor. Trapped ions, silicon quantum dots. I just mentioned of this size effect. So we all know of silicon, which is a semiconductor, but if I make it smaller and smaller and smaller, make it like a dot. So that means the normal thing we see here is infinite in all dimension. What I mean by infinite is a macroscopic thing. Okay? But if I reduce the dimension, for example, I take this slab and I reduce it in one dimension, then it can be a completely two-dimensional object. People have also made such thing. For example, in case of graphene, which is just single atom of carbon and making a sheet. Now I make it reduce the dimension in all direction. Then what I get is what is known as quantum dot. So there you expect also the quantum effect will prevail. There are other platforms as well. We don't know which platform, so they are all runners. Which one will win the rest, it's still not very clear. But what is important in all of them is a materials design. Because for classical computer you already know. And in fact, if you think of semiconductor industry, it started in some 1950s. You are here, you can vouch for it. It took so many years to develop and come in a full-fledged glory. I think we are in the same situation in terms of all quantum technology. We have a lot of confusion, things are not settled, but we are in the same thing as your semiconductor industry in 1950s. So the hope is what semiconductor industry now, maybe down the line, we will also reach that stage. So therefore, there is a lot of importance of materials design. So I think I will skip the next slide and I will tell you a little about materials. The importance of materials in human civilization is enormous. It is so much so, if you actually have to demarcate different ages of human civilization, you actually talk about some material. You start with the Stone Age. Stone is a material. So that age you actually associate with some material. Similarly, the Bronze Age, the Iron Age. So as the human civilization has moved, you are demarcating each of these ages with some material. So it is so important. The plastic and the modern age is your silicon age. So how many of you know the name of Leonardo da Vinci? I think here everyone. So he was, of course, a great painter, but he was a philosopher, he was a thinker. And what he said, that's his prediction, is what is known as a designed materials age. That is the precise quote from him. When nature finishes to produce its own species, man begins using natural things in harmony with this very nature to create an infinity of species. So that means that there are materials which exist in nature and they show certain properties. Suppose I want to change that property, then I have to engineer something. And this engineering may become so much that I actually am designing some entirely different material, but with some targeted property. So it is not that someone has given me the material, I characterize, get its property. It's a reverse engineering. I actually have in mind some material and I reverse engineer to find an appropriate material for that. So you can imagine, how visionary they were. So he thought that is going to be the future age. The age should be called as a designed materials age. So that now brings to the title of my talk called Quantum Materials. Now I told you that if I can suppress all the thermal fluctuation, the world will be quantum. So that means if I am at the lowest point of temperature, which is 0 Kelvin, then all material should be quantum material. So what is so special about quantum material? So these are these materials which even at finite temperature, not at 0 Kelvin, they actually show properties which are driven by the laws of quantum mechanics. So therefore, they are different and they are called the quantum materials. Even at finite temperature, their properties are dictated by the laws of quantum mechanics. Without that, we cannot explain that. So I have shown some of the examples. Superconductor, I will actually have one example on that. Magnets, some of these other jargons, which I think explaining it will be difficult. But bottom line is their properties, even at the finite temperature, they are governed by quantum fluctuation, quantum entanglement, quantum coherence, and etc. So as a quantum particle, even if I have stopped the thermal fluctuation, there is always a quantum fluctuation. Even at 0 Kelvin, it actually survives. Quantum entanglement. So as a quantum particle, I can entangle. So if I was a classical particle, I can interact only if someone is in my neighborhood. But as a quantum object, since I also have a wave-like nature, I can actually interact with anyone. And that's an entangled state. If everyone in this auditorium were a quantum object, everyone will start interacting with the other one, irrespective of our distance. So finally what will generate is a completely entangled state. And that you cannot have such a correspondence in your classical world. So it's a very different world. We are, all our ideas, all our preconceived notion, everything we have to really dump and come into a new world. So these, finding out such material actually needs hand holding. That's why so many scientists, they are working together. For example, you need a person to make the material, characterize, even if you have made the material, to get into a form which is a device form, you need lot of fabrication, prototype, and also very important, some of the theoretical input. Because before you start doing all of these, you actually need to have some idea of it. For example, if you are looking for a new material, you need some lead from a person who can calculate and tell you. Because if you want to try to do it in the laboratory, you need lot of consumable, you need lot of manpower to make it, and maybe you will fail. In the computer, there is no consumable, nothing. So this is just to guide these people. So what you need is what is shown here is a mutual collaboration between people working in the lab, the experimentalists, the theoreticians like the famous S.N. Bose, who will give me the formulation, and people like me who works on computer, but classical computer, to solve such kind of algorithm and tell if you can make such a material, you will see these kind of properties. You can stop me at any point of time because I am really going slow, and whenever people think can be animate, I will, if you just give me a little more time, I will show some example. You have also made previously said about this negative. What is this negative sequence? No. So one thing, for example, I will not touch upon this. One big concern about making a quantum computer and a big bottleneck is what is known as lack of coherence. I talked about this entangled state. How long I can keep this entangled state? That is what is known as decoherence. The whole thing will be spoiled by that. Absolutely. So there is a limitation in the sense, in the quantum computing language, in classical you say bit, there they talk about qubit, and how large qubit of this quantum computer will be actually depends on how well I can manage such decoherence. It's very much in trial and error method, very much. And not only that, I gave you, these are motivation. If for a quantum computer to work, you have to have a completely new algorithm, meaning the software part you also have to work. Whatever is your classical algorithm will not work in quantum algorithm. So this kind of consensus that is getting out, not all problem will be good for quantum computer. Maybe there will be some category of problem that will be good for quantum computer. So classical computer will never be obsolete. So there will be certain class of problem for which we will use classical computing and certain class of problem for which we will use quantum computing. So that's the kind of, it's a evolving and changing situation, but that is kind of the current state of it. I don't know. Yeah. So what I will do is basically, so many of the properties of these materials are actually at the quantum level, they are governed by electrons. You have heard the name of electron, right? Because electron is really the glue that binds atom together. How the bonding between two atoms happens, the responsible factor is the electron cloud that overlaps. So it's the electron is kind of a glue that will bind atom together. So the bonding and every property are given by the electrons. So many of the properties, exotic properties that you find in quantum materials, electrons are the responsible factor. So the motto is to calculate the electronic properties, the properties which are governed by electrons in a what we called as an ab initio way, don't bother about it. So design new quantum materials, as I have already explained, with a tailored functionality through computation, through classical computation. I think there was a question whether really such material will exist or not. So, and for that we use lot of computation, classical computation, and all of the power of such kind of, this is kind of the architecture of such, which is called a high performance computing cluster, and the performance of it is in terms of the flop, how many floating point operation your computer can do in a second. And so these are in terms of some teraflop. So the peak performance of the computer is measured by that, and these are some of the places. This is actually quite outdated list, but the more recent news is India is having a national supercomputing mission. The goal of this mission is to basically establish some petaflop machine in different corners of India. And this is a news from actually last year, that we are in the third phase of this national supercomputing mission, and as a part of this, 9 more supercomputers will be commissioned and installed, which is shown here. This is a list of 9 institutes, and along with different IITs, also the name of Bose Center figures. And right now we are in the process of installing this machine. So 2024, there will be a petaflop scale machine also installed at Bose Center. Okay, so now I will show few examples. I will try to be brief, and I will try to give you just the idea without giving you lot more details. So how does this computation can help us? Our target is to design material, but we have to go step by step. We cannot be super ambitious at the very beginning. So the first one is understanding the structure property relationship. I know a material, I know the material structure, and I know its property. So what is the link between it? First I have to understand, if I have to make some new thing, I have to first understand what is already existing material, existing properties. And I mentioned of superconductivity. How many of you have heard the name of superconductor? Not that many. So, you know a metal, right? If you cool down the material, this metal, so metal is something which can conduct electricity, right? Is that okay? Right? So, of course, it doesn't conduct it 100%, right? There is some resistance to it for conductance. So, as I cool down this metal more and more and more, I reduce this thermal effect more and more and more, actually its conductivity increases. And ideally, if I can reach 0 Kelvin, and if I have a perfect metal without any impurity or anything, I should actually get infinite conductivity. Okay? But I don't get it because there are some impurities. Now, who will reach 0 Kelvin? That is not of use for me, right? No, nothing will function. You are very right. So, who will reach absolute temperature, and we don't need that. So, that is useless. But then the superconductors comes to rescue, which even at finite temperature actually shows 0 resistance. So, at finite temperature I do have 0 resistance. So, when it was discovered for mercury, this temperature was 4.2 Kelvin, still very low temperature. It is not 0 Kelvin, but it is 4.2 Kelvin. And I hope you can see this. Over the year, there is a tremendous race to increase this temperature. Suppose I can make it room temperature, brilliant. I have this material, I use this material, there is no resistance at room temperature. I can make with this material superconducting railway track. There will be no friction, nothing, no resistance. So that will be actually a wonderful thing. So you can see what is shown here in this plot is the year in the x-axis and these transition temperature, superconducting transition temperature in the y-axis, and these are different kind of materials that are being made. So far, under ambient condition, that means under ambient pressure, the family of compound that show the highest temperature, your room temperature is some 300 Kelvin. It could reach as high as somewhat more than 150 Kelvin, are these compounds which are based on copper and oxygen. And there is an entire family of this compound. All of them has copper and oxygen. I think some of you who have chemistry, periodic table, you know the copper is written as Cu, oxygen as O. So all of them has copper and oxygen, but they have also some other element. And these temperature which I have shown here, they are very different. For the compound having lanthanum, if you remember your periodic table, that's 40 Kelvin. But instead of lanthanum, if I use mercury and barium, that goes to 90 Kelvin. So that means this material, while it is 40 Kelvin, this material is 90 Kelvin. So somehow I know this structure, this material. Since I know this material, I know its structure, I know its transition temperature, which is a property. So I have structure and property. I have to make a connection between two. What governs? What changes between this and that? Because copper and oxygen is same between the two material, and that is considered to be actually the important thing for superconductivity. But I replace something else and the transition temperature becomes double. And as it looks like, that these materials, now I will show something which is known as the crystal structure of such materials. They have planes of copper and oxygen. Copper atom surrounded by 4 oxygen atom and in a planar structure like a sheet. So in between this stacking of this sheet, which is shown with this pink colored plane, there are these, let's say, lanthanum and also some other oxygen which is actually out of plane of this copper oxygen, the pink shaded plane. And as it turns out, without giving you any details, the only thing that is important is this bond length, this distance. Now I am really looking inside the material, how exactly the atoms are sitting, to have an understanding. A material is there, but the material from outside is that, but if I go to its atomic distribution, what are the atoms, how they are sitting, that actually plays a very important role. And what turns out to be very important is this distance between the atom which is out of the plane, you can see these yellow balls, and this pink shaded layer. And as it looks like, that's what our computation showed, the larger is this distance, better it is to boost the TC. And we also gave an understanding why is that. That's a bit technical, so I will avoid that. So these computation then can help in providing a missing link between structure and property. So that's our first step. Now the second step will be, I will skip this. So it's an effective tool to uncover structure property relations here. The second class of problem, suppose I know the material, I want to predict its property. I am getting more into prediction. So the material is known, someone has made it, but you don't know what it is useful for, so they have not really measured all the properties. Can you do computation and already predict some interesting property so as to motivate the experimentalist, to guide them, you just go and look for this property. And what I will show here is, I will spend a bit of time to explain this graph which is shown here. So these are some transition metal. How many of you know the periodic table in this hall? Quite some hand, not all of you. But I think the periodic table is the biggest discovery of human civilization. Even if you are not a scientist, periodic table is fascinating. When I was a student, I never realized it. And it's a pity that Mendeleev didn't get the Nobel Prize. Periodic table is the origin of everything. So transition metal, so these things actually have some of its electronic orbit which remains unfilled. So you have these electronic different orbits, and some of the orbits remain partially filled and the outer orbit gets filled. So this object here is iron, which is actually a transition metal, and these iron are connected by different organic ligand. So iron is an inorganic object and I am connecting it through some organic ligands. So these are like which are what is attached to it. Now this iron here is actually iron 2 plus ion. You have heard about ferrous and ferric. So it's iron 2 plus, and therefore it has 6 number of electron. And since it is surrounded by this ligand, actually the energy level, they get split in this way. Now I have 2 possible ways to arrange such 6 electrons. One possibility is I just paired them up down. Electron has a spin and spin of half, so it can be either this way or that way. So I am showing it as up or down. So in this way, if I pair them up, then the total spin of this object will be 0. It will be a non-magnetic object. On the other hand, the same thing, if I can arrange in a different way, then it becomes a magnetic object. So just how I am arranging this electron, I can actually drive a non-magnetic to a magnetic thing. And it is possible to drive this by changing temperature, by putting pressure, by shining light. So you can see I can basically drive a magnetic to non-magnetic thing by external perturbation. That is very important. I have to make a device. You all use device. But aluminum is not a transition metal. I want to play with magnetism. Okay. So aluminum will be like an alkali. I don't want such kind of object. I want a transition metal. I want, therefore, I mentioned unfilled shell. Okay. Chemical property kichu change kore na, physical property change kore. ম্যাগনেটিক প্রপার্টি চেঞ্জ হওয়ার সাথে সাথে তাদের কালার চেঞ্জ করে, কারণ এইগুলো একটা মানে একটা ক্রিস্টাল ফর্ম করে এবং সেই ক্রিস্টালের একটা ব্যান্ড গ্যাপ থাকে, সেই ব্যান্ড গ্যাপটা ডিসাইড করে কালার অফ দ্য মেটেরিয়াল, কাজেই তার কালারও চেঞ্জ করে। সো আই উইল শো ইউ। So I am showing here, so what I showed in the previous slide was like a molecule. This is a molecule, right? This is a big molecule. This was an isolated object like a big molecule. Now what I am doing here is I am putting one molecule next to another one and I am forming a connected chain which is known as a polymer. So I connect all of them. So suppose I have this transition from non-magnetic to magnetic at this site, at this site, at next site, and next site, and next site. If I can do such a way, then the whole thing becomes what is known as cooperative. All of us, like in a prayer or what you do up there, chorus, everyone starts singing together. That's a cooperative thing. If it becomes cooperative thing, without getting into the details, I am just giving you the phenomena. This non-magnetic to magnetic transition even happens with what is known as a memory effect. I just said by temperature you can actually drive this transition. In the heating path and cooling path, actually that temperature this will happen is different. As a result of that, the material actually remembers whether it was a heating path or cooling path if I fall in this temperature. So then I can use it as a memory device because it remembers whether I was in a heating path or in a cooling path. And I am showing you, this is actually an experimental data. This is not a cartoon that I have drawn. I said actually the color of the sample changes. So you can see the color of the sample, whether it's in a non-magnetic and magnetic in the same temperature range if I fall within this. Okay? So that is of tremendous application, you can already see. So what we did, we actually did some computation on some known material and we predicted such properties in those materials where it has not been tried. So they will be then the potential material which will show such kind of non-magnetic to magnetic transition with a memory effect. So they have not been really tried for it, but the material has been made. So the material is there. So our calculation can guide us that you use these materials for this purpose. So I think I will finish with the last one, which is the most important one. So it is, this computation helps in designing new functionalities in known materials. Now the last one, can we really predict new materials altogether with some tailored property, the properties that we have already decided? And for that, the example I will use is magnetic materials. all of you use magnetic materials in your everyday life. There are examples, I don't need to give you the example. Tape recorder, hard disk, magnetic storage you are using in your cell phone, everywhere. How many of you know that magnetic materials are a rarity in nature? Only 5% of known inorganic compounds are actually magnetic. So the whole world is in dying need to find new magnetic material. And not only new magnetic material, we also want something which are ferromagnet like iron. They will be like iron, but they will be what we call as half metal. Iron is a metal as well as magnetic. It conducts electricity and it is ferromagnet. So that means the electron which has two different spin degrees of freedom, so it conducts the electricity both for the upspin as well as for the downspin. So I can use only the charge of the electron as a source of information transmitting from one side to another. But since the electron has a spin, what if I could use the spin of the electron also? And that can be used if I can filter in a sense that I will have only the upspin electron conducting electron, not the downspin electron. That would have been wonderful, because then in addition to charge of the electron, you can actually use the spin of the electron also to carry information. So we therefore, this is what I call as targeted property, and you need new materials. And what we did, to cut the long story short, we actually used machine learning for this purpose. How many of you have heard the word machine learning? It's there in newspaper every day. So machine learning is nothing to do with physics, chemistry, anything. Machine learning is nothing but a pattern recognition. So for example, in this room, some of you said you are Bengali speaking, some of you said you are English speaking, or whatever other than Bengali speaking. So this is like a sample. So I try to characterize all of you with certain, characterization, and I say if you are this, you are a Bengali speaking. If you are this, you are not Bengali speaking. That's called a learning set. And once I learn this, machine learns it, that is an algorithm, then I bring a new person and ask the machine, can you tell me whether this person is Bengali speaking or not Bengali speaking? That's called machine learning. Machine learning you can apply to any different thing, any different domain. It's just a way of pattern recognition. So what we did is the following. We learned this pattern from some material which we already know, and we know their properties, and use machine to learn this connection between this material which has certain, which is called attributes, certain characters. Then they will show us this kind of property. Now we design in computer some new material and ask the machine, will this material will have the desired property? And in fact, we predicted several new materials. I will skip all of that. And we predicted 33 new materials. And I'm very happy that in Bose Center, my colleagues are actually making, and 3 out of this 33 has been already made. So you had to really, I think there was this question, you had to really work hand in hand together with this experimentalists. It's a feedback mechanism. In fact, the material which we predicted they made, we also predicted their crystal structure, how exactly the atoms will be sitting, and there was slight difference they found. We went back, we corrected our thing, and we actually now are in agreement with each other. So you really need to have this cross dialogue to make these materials. So I will just finish with this one liner, that material matters new materials in design is one of the goals of the modern day research. So thank you very much for your attention, and I think it will not be right if I don't put this acknowledgement slide, because of course I did not do all this work by myself. There are numerous students, there are numerous colleagues who contributed to whatever I presented today. Thank you very much for your attention.
Now, it was a wonderful talk as far as I am concerned, because I started my career more than 50 years ago using Josephson junction for a computer. So that was superconducting also, but different mechanisms entirely. So, but this is the future. What he talked about, I'm sure that we'll make it. The human being, particularly from India, they will make a lot of contributions to make this computer, this quantum computer. At least in my mind, I have no doubt about that. We'll do a tremendous job, I think greater than the USA even. So right now. So this was a wonderful talk. And now, if you want to ask any questions, any more questions,
It is, as I think Professor Lyre said, it's actually futuristic, it's open-ended. If you want to see its effect now, I think you will be disappointed, and that's what I said, the situation should be compared like with 1950s with your semiconductor industry. So you have to still give time, and as you can see that a lot of people are working on it. If tomorrow you want the technology to be in the market, that is still futuristic. But people are using, for example, there is a lot of progress already made with the quantum sensing, where the properties of quantum mechanics people are used in sensing in metrology that possibly will have, you will see certain effect. For example, when we have the information passing from one side to another side, so there is something which is with the secrecy of the information. Okay? If you use, instead of classical algorithm, quantum algorithm, your secrecy will be more intact. What people are fighting with is also your information should be actually delivered intact, meaning one is secrecy, someone should not get this information, but also the accuracy of the information should be there. And what people are fighting it with is accuracy of this information. So there, if that can be really somehow defeated, then of course there will be a lot of application in our national security and everything. That's why the whole world is after it. So the application domains are many, whether it will be immediate or it will be after 50 years, that the time will say, but among these, some of will be sooner, some will be later. That's all I can say. No. Sorry. So this artificial intelligence and the machine learning is nothing to do with quantum computing. Nothing to do with quantum computing. Absolutely different. This is a way of pattern recognition.
Another
হ্যাঁ, সো যে কিউবিটগুলো বানানো হয়েছে সেগুলো is all like 16 qubit, 40 qubit. So these are all below 100 qubit. Size দেখতে it is not compact like the way you are thinking about. For example, the supercomputing qubit, the whole machinery is huge. So people are still not thinking about that tomorrow it will be in market, because you will have all the designing thing when you are sure of the algorithm. That is a classical computer. I'm sorry if that has created some confusion. Yes. That is not a quantum computer, so that is not a qubit machine. That's a classical computer, a bit machine. So you really, it is still in the lab that you are doing. Okay?
Right now, apart from the IBM and Google,
So all of the things are with Microsoft, Google, all these companies are in business. In lab there are, no, it is not. They are, if you have to manufacture, you have to know how to scale up the technology. That is not there. No, this is absurd. It's absurd. So we are definitely not in this stage.
May I just say, this is something we should know, all of us, that any new technology, they're showing the feasibility aspects. And then actually comes a lot of things before it makes the market, like just very mundane things, the reproducibility of the productions, the reliability of the devices. Those are the things which takes maximum amount of time. In IBM, they had a research division.
As you said that you people already theorized some kind of material. Okay, so how you tested that without?
No, that is what in the last example I showed, we predicted those materials. We had no idea whether the materials can be made. It's our prediction. So our theory will be incomplete unless there is an experimental colleague who holds my hand and says, okay, I will try it in my lab. The advantage is, as an experimentalist, there is n number of possibility and you cannot try everything. If there is a promise already shown by some calculation, then you have more guidance. You screen a lot of possibility and tell only this few can show such kind of properties. No, it is really not in that stage. First of all, the material that we made was not as to be used as a platform for quantum computer. Okay, the material we made is for a different purpose. Okay, so not everything is geared in making quantum computer. That's a completely wrong idea. I gave you the example of quantum computer because most of you are used hearing that. So they are using basically both Google and Microsoft, they are using the superconducting qubits. It's based on the platform of superconductors. I mean, that looks to be promising for them, but there are lots of people who are working with the diamond in centers as well. So it is still not very well established. So even the platform is not well established.
Yeah, it's a wonderful talk actually, that we are in the game, it's not that IBM is in the game. So it's a different world right now.
And even for IBM, they have to rely on some scientists to give their thing, So typically it's of that's already the highest that you are thinking of is like the 100 or the ballpark of 100. No, it gives problem. You cannot actually stabilize such quantum entangled state.
Well, this is fantastic, I think we should stop here. Because,
yeah, it's already pretty late. And
ask her while going downstairs, because...
you can also email me. I think my email address is with Professor Laidi, and if any one of you want to send me email, please feel free to do that. And thank you for staying back so long.
It's a wonderful talk. It's a futuristic talk, but it's a wonderful thing.